Okay, so here we're just going to continue where we left off last class. So we're going to be doing we're continuing section 12.3, implication. Oh, and let me pull up my solutions. Okay, so here we're just continuing section 12.3. Okay, so here we want to note that it's important, or let's see, so it is important to note that P implies Q is not the same as Q implies P. Is not the same as Q implies P. Okay. So we're going to verify this with the truth table. All right. So we set up P and Q already. Okay. Now, implication is always true except true implies false. All right. So true implies true is true. True implies false. That's the only case that's false. Everything else is true. Okay. Now, if we do Q implies P, true implies true is true. False implies anything is true. True implies false is false. And false implies anything is true. Okay. So just to kind of, for that second one, when we did the Q here, so when we did Q, we said Q implies P. We're saying true implies true is true. False implies anything is true. True implies false is false. False implies anything is true. That's how we did this last column over here. Okay? So the implication Q implies P is called the converse of the implication P implies Q. Okay? So the implication Q implies P is called the converse of the implication P implies Q. Okay. So this example accesses the constructed truth table for the statement form P implies Q and its converse. I think we just did this. Okay, well, we can do it again. So if we do P implies Q, true, it's only false when we do true implies false. So this is true, false, true, true. So this is the first column that we did. Then we're going to do Q implies P. So true implies true is true, false implies anything is true, true implies false is false, false implies anything is true. So this is the second column. So now and, remember, and is true only when they're both are true. So if we look at the first one, are they both true? Yes. Are they both true? No, no, and yes. Okay. So here, so just in the last one, notice that they're not the same. Yeah, that's it there. So the biconditional, the statement P implies Q and Q implies P is referred to as the biconditional, which is written P is logically equivalent to Q. Okay, let's look at it. So the statement P implies Q and Q implies P is referred to as a biconditional, is referred to as a biconditional, which we write as P is equivalent to which we write as P biconditional Q. So we want this guy and this. Okay. So that is true when they're equal to each other. Okay. So if we look at P and Q, are they equal? Yes. Are they equal? No. Are they equal? No. Are they equal? Yes. So the biconditional is true when they're equal to each other. Okay, so now we can talk about order of precedence. So as we do these, as we kind of do this prepositional calculus, the order of precedence for logical connectives is the following. Okay, I don't think I need the lines here. So the order of preference, or let's see, precedence for logical connectives is, so I'm going to add something. This isn't necessarily a logical connective, but typically we do parentheses first, and then we'll say not, and then or, and then the implication, and then the biconditional. Okay. Order of precedence, so order of precedence, and these guys. So then this means we apply the not first, or the parentheses first, then the not, then and then so on and so on. So this means we apply parentheses first, then the not, then and, then or, then the implication, and finally the biconditional. Okay, so that's the order in which we approach, like if there were no grouping symbols, this is the order in which we do things. So for example, we're actually construct a truth table for the statement form. Okay. So notice we lined up the columns under each, based on each symbol. Okay, so these are based on the symbols. Okay. So if we're looking at the left, it says construct a truth table for the statement form this and this in a more efficient way. So we're doing like a shorthand notation, or a shorthand version. So we would do not P first, so not P, so we're just doing the opposite of P. So we're saying false, false, true, true. And then we want to compare that column to Q. So and is true when they're both true, so they're not both true, they're not both true, they are both true, they're not both true. So it looks like maybe we'll number it like this. This is 1, and then 2. We did this one third. It's the third column we did, and this was the fourth. Okay, so now if we look on the right, if we do parentheses first, that means we have to do the and first. So P is true and Q is true, so we're going to compare columns 1 and 2. So this is true, this is false, false, false. This is column 5. Then the last thing is to negate that column. So then we're going to get false, true, true, true. This is 6. And actually I meant to do the following. Different color. Okay. So the final column for the first one is this column 4. And then the final column for the second one, I'm going to try something. Just copy this. Is this one. Okay. Notice that they are not the same. So we'll say we note that the truth values in 4 and 6 in these columns, the truth values are different. So that means that the order is important because they're the same statement forms, but we did different orders and they produced different results. Okay, so the order that we do these is important. So in this example, we're asked to insert parentheses in the statement below to show the proper order for the application. Okay, so if we're going order of precedence, the first thing we want to do are the knots, so we would do this first, all right? So next we want to make sure that the ands get done. So the first and is here, so we would like to do wait a minute. Yeah, she has it has that, there's another one that says that either one works. I'm a little skeptical. But anyway, so we want to do the ands next. So now that forces us to do the knots first. Then we do our ands. So the or takes precedent over the implication, so we want to do this or next. And then now last thing that's going to happen is the implication. Okay. Okay. So we want to move into 12.4, logical implication and equivalence. So let me open up a copy of this. So let's consider the simple statement, P implies Q, and not P or Q, okay? So let's construct truth tables and compare these two. So if we do P implies Q, so true implies true is true, true implies false is false, false implies anything is true and true. Now, if we do the next one, we have to do not P first, so it's going to be false, false, true, true. We want to compare, so this is 1, or here, let's be consistent. So we're going to say 1, 2, 3, 4. So now we're going to compare column 4 to Q, which is column 2. So we're going to compare them with an or. Or means at least one of them is true. So at least one is true, neither one is true, at least one is true, at least one is true. So notice the final columns I think are the same. This column is the same as this guy. True, false, true, true. Okay? So because they're the same, then that means we can use them interchangeably. If we're given implication, we can rewrite it as not P or Q. And if we're given not P or Q, we can rewrite it as implication. So let's make a note of this. So we note that 3 and 5 are the same. Okay? 3 and 5 are the same. Okay, so again, that means we can use them interchangeably. So we have some definitions. Let's introduce some lines. Okay. So then we say two statement forms that have the same truth tables are called logically equivalent. So, or, yeah, two statement forms that have the same truth tables are called logically equivalent. Logically equivalent. Okay. So then we have this term called a tautology. This is a statement that has truth value true regardless of the truth values of its component. Okay. So this is a statement that has truth value true regardless of the truth values of its component. Of the truth values of its component. Okay. So then, conversely, we would say we can talk about a contradiction. This is a statement that has truth value false. So this is a statement that has truth value false regardless of the truth values in this component. I'm just going to copy the rest of that. Okay. So here we actually show that P or not P is a tautology and that P and not P is a contradiction, okay? So let's kind of go ahead and create another line. So let's do not P really quickly. Not P is going to be false and then true. So this is like 1, 2, this is the third column. So we want to compare column 3 to 1 with an OR. So is at least one true? Yes. Is at least one true? Yes. So we see that it's a tautology. Then we're going to compare P and not P. So we have not P at 3. We're going to compare 3 and 1 with the N. Are they both true? This is false. Are they both true? No. This is the fifth column. So no matter what the value of P is, so here. So no matter what the value of P and not P, what their values are, so no matter what the values of P and not P are, P or not P is true. Which is a tautology. Okay. And then, anyway. So we have P and not P is false. A contradiction. Sorry about that. Let's see the time. Go away. All right. So we want to show that not P and Q is logically equivalent to not P or not Q. What law did we apply there? Okay, so just, think about that. What law? This is something we've talked about before. See if you can tell me what law it is. Let's see. So this will be column 1. This will be 2. So if we did parentheses first, we have P and Q. So that means they both have to be true. So this is true, and then the rest are false. So then if we negate that, that's going to become false, true, 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 right? This was column 3, this was column 4. So now if we do the not P first, we get false, false, true, true. This is column 5. Not Q is going to be false, true, true. This is column 6. So then or means at least one is true. So at least one is true, no, and then true, true, true. This is column 7. So the final columns, let's see. This is one of them. And then 7, this one. Okay. Notice that these two are the same, and we actually, didn't mean to do that. We actually use De Morgan's law here. That's De Morgan's law. It's like a distributive property of a not over and an or. Okay. Okay. So we have P biconditional Q is true whenever P and Q have the same truth value, meaning they are both true or both false, meaning they are both true or both false. So then P, this kind of arrow, Q. This means P is logically equivalent to Q. P is logically equivalent to Q. This happens if and only if P biconditional Q is a tautology. This happens if and only if P biconditional Q is a tautology. So then the contrapositive, let's see, so the contrapositive of the statement P implies Q is the statement not Q implies not P. So some logical equivalences, not P is P, so there's a double negation, so on and so on. How many more we have? Oh, we have a good amount. Yeah, it keeps going. Okay. So actually, I think I will use this as a stopping point. It doesn't hurt to know these, and a lot of them are kind of natural and they make sense, and you're not too difficult, but it doesn't hurt to know this. Okay. But we will actually end the presentation here, okay, gentlemen? And so, you know, your substitute should have some material here for the remainder of class. Okay? So with that, enjoy the rest of your weekend, and I will see you all next week. All right, have a good week.